All right, hi everyone. My name's Alex. I'm here to talk to you about how at Octopus Deploy we've been evolving our code base as we scale. I don't think it's going to be quite as exciting as some of the AI content in the news, but we'll give it a go. We'll see how we go. So my name's Alex. I'm a senior software engineer at Octopus Deploy. I work in a team called Server at Scale. This is relevant because my team is tasked with taking what Octopus Deploy has now and really scaling it out for our enterprise customers. We've got a bunch of stuff to get through tonight, so I've made us a bit of a roadmap. Essentially, this is going to be a tour of some of the problems that my team have encountered as we try to scale up, how we've solved them, and what we've kind of learned from them. So we're going to start off with a little bit about what I mean by trying to scale Octopus out and what Octopus Deploy does. So as a company, we were founded in 2012. It was quite a while back now. As you can imagine, the landscape of deployments and the complexity of deployments has changed a lot in this time. We've done about 150 million deployments to date. We've got about 600,000 machines that are using our little agent. We call it a tentacle, Octopus tentacles. And we've got some really cool customers. I don't think they're on this slide, but when I found out that Blizzard were one of our customers, I had an absolute fangirl moment. So that is very cool, and I mention it at every available opportunity. So we do cloud deployments at scale. What we are working with is enterprise companies who have just absolutely massive scale. So looking at these kind of things, these are the concurrent numbers that we're trying to hit. This is usually within a 24-hour period, something like 16,000 targets. The deployment target is essentially your infrastructure that we are deploying to. So your VM, your container service, whatever you want. So one of the sort of fun things for me about Octopus Deploy in particular is that the kind of problems of scale there are quite different from the problems that I have previously encountered. The kind of software that does deployments is kind of a different beat from the kind of web app stuff that I have. It's essentially a problem of coordinating a lot of different complex interactions with all of these targets and making decisions based on those interactions, right? So it's not a particularly user-heavy flow. So one of the other super fun things that we do is, because our value proposition is basically we will run arbitrary scripts on your infrastructure securely, compliantly, reliably, auditably, in whatever sort of regulatory environment that you need. A lot of our customers choose to self-host Octopus Deploy. And so what that means is that while we have cloud offering, whatever we build also has to be able to be run by our customers on their infrastructure, usually in the cloud environment of their choice. But it means that we are explicitly not cloud native. So to solve these problems, we can't use fancy cloud stuff because we can't ask our customers to run a service bus for us. We can't ask them to do a lot of stuff. So at the end of the day, really just our application, our database, and all of our little remote agents running on the infrastructure. When we talk about core problems, right, I'm not talking about stuff where we made a whoopsie, I'm talking about the kind of emergent properties that happen when you have your software used more and more and more, and you start to see the ways that it's going to creak under that kind of strain. Like I mentioned before, like a CRUD-style app, like a typical web app that's very user-oriented, CRUD in terms of like create, read, update, delete kind of operations, the performance characteristics of those are very different from the performance characteristics of deployment software. In particular, it's really, really bursty. So you kick off a deployment to all three of your environments. That's going to fan out into a lot of different tasks for a lot of different things. So the nature of that work can be that it scales out really quickly. And again, we're coordinating all of those multiple agents. Those things aren't necessarily running on our infrastructure. They are running on our customers' infrastructure. And it's not always a nice cloud environment either. It's pretty frequently actually devices out in the real world. Examples are medical devices. We use devices in hospitality, even car washes, actually. And so coordinating this kind of remote work in these kind of constraints, especially given that we can't use fancy cloud technologies, it's kind of a fun problem. So I'm going to talk a little bit about how this whole concurrency concept plays into our scale problems. So when we're talking about complexity, we often talk about complexity in software, and we're often talking about it as accidental complexity. We built something, but the way that we built it is harder than it needs to be. Maybe we planned for scale that we didn't need. Maybe we tried to solve a problem that we didn't have, but someone in your team had at their past job. What I want to talk about here is the essential complexity of the type of deployment software that we deal with, which is that ability to deal with input from a lot of different things in a range of conditions and still come out with the correct behavior. So correctness is absolutely key for us. We had an incident recently. I wanted to talk about it here, but it doesn't quite fit in because it was actually the result of a stupid decision that we made. But one of our customers was on the call with us. We were trying to ascertain at that point whether we were actually doing things incorrectly or if we were just kind of logging things out of order. This customer said to us, hey, look, we do blue-green deployments, and we think that this execution is happening out of order. We are really, really worried because in a blue-green deployment, you bring up your new infrastructure, you start running your traffic through it, and then you bring down your old one. And he said, if you bring down the old infrastructure without having successfully brought up the new one, there will be no bank. Guys, there is no bank. And so the thing that just echoes in my mind whenever I think about the importance of correctness is there will be no bank. And so that correctness and the complexity is basically essential. That is what you are paying us to solve for you. And so it is kind of a domain modeling problem because that is what we're here to do. So I'm going to introduce you to this guy. This is essentially one of the things that we use in our Codebase to make it easier for our developers to think about how a lot of this complex bursty work gets done. I'm going to introduce it now because I'll probably refer to it a bunch, and so I want to so hopefully you'll have a bit more context around what I'm saying. Essentially, this ServerTask thing is an interface in C# language, but it provides developers with a whole lot of stuff for free. So it is an item that can be queued. It is essentially a wrapper. Let me try that a bit closer to the mic. It's a wrapper around an arbitrary bit of work that allows us to queue and control how many things that are executing concurrently. We have some spectacular stories about what happens when you don't control the number of things that are executing concurrently, but this is just something that in general people use so the developer can go on to focus on whatever fancy functionality that they're building. And in particular, my team, this has become our best buddy as we've been working on this thing and trying to get this particular part of our Codebase to scale. So I'm going to be talking about concurrency as well. Concurrency is just the idea that multiple things are executing at the same time. Concurrency isn't really a bad thing by itself, right? It's just a concept. There are multiple ways concurrency can go wrong. And this time, happily, this is not a deadlock problem. I've dealt with deadlock problems, those are not fun either. But we're specifically talking about the kind of race condition problem that happens with concurrency. So we've got this beautiful little diagram that our design team made. What you can see is, looking at thread 1 and thread 2, generally concurrency is going to show up because multiple threads read the same item from the database, they mutate it based on whatever they're trying to do at the time, and they write it back. But what you can see in the example, right, is thread 1 writes before thread 2 does. This means that whatever thread 2 has done to that object is likely incorrect because it is missing any changes that thread 1 did. The delightful thing about race conditions is that these are really hard to identify, right? This doesn't necessarily result in an error at the point that this kind of out-of-order execution happened. This results in an error somewhere down the path because your data is inconsistent or incorrect. It's basically the problem that the result of whatever you're executing isn't actually deterministic, right? Like, it depends on the timing. And that can be really hard to replicate because you don't necessarily know, because remember, you don't see the problem until way down the path. You don't necessarily know at what point you had some sort of timing problem. So generally, best thing you can do is avoid it, right? And there are lots of tools and techniques and stuff that people use to avoid getting in the problem in the first place. But as always, there are a bunch of trade-offs to consider as to what we're going to do and why. So what I really want to talk you through here, going through some specific examples, is the trade-offs that we chose to make, and then essentially the ways that they bit us in the ass a little bit down the road. So we're going to talk about problem number 1, our cluster-wide mutex. We're going to talk about the concept of pessimistic concurrency and how we modeled that in our database. So, cluster-wide mutex. You'll remember before I said Octopus server, we have the database, we've got an app, that's it. In order to get more throughput, in order for us to be able to execute multiple things concurrently, we offer our customers the option to run Octopus in what we call high availability mode. It's horizontal scaling. The cluster-wide mutex is an application level concern that we built to control which nodes in a cluster are executing something in particular, or have essentially like a mutation log on something. We chose to model it in the database because remember, that is the only shared resource that we have between the multiple nodes of the cluster. Theoretically, we could communicate in between them, but there are some failure modes with that that made the database one a little bit better. A little bit better choice for us at this point. And while I was sort of researching for this talk, I found out, I must have learned this at uni and completely forgotten, but Mutex actually stands for mutual exclusion. So essentially it's the idea that when you hold the mutex, you are excluding anything else from mutating that object. The word mutex has nothing to do with mutation, which was wild to me. So, how did the cluster-wide mutex fail? Well, one of our customers came to us, and this is a customer who self-hosts, and they said to us, hey guys, the database failed over. What did you do? And we said, that is a great question. We don't know. And they sent us through a bunch of data. So one of the things that was immediately notable to us was that this had happened after a 10-day long deployment. This is one of the fun things about enterprise deployments. If a customer says their deployments take 10 days long, then that is not our place to argue with them. Sure they do. Great. So what happens? What we found was the database had failed over because it had run out of disk space. It had run out of disk space because the transaction log had eaten all the disk. What had happened was this, that cluster-wide mutex, that was implemented by opening a transaction in the database for the duration of the deployment. After 10 days, the transaction log in SQL Server is essentially like SQL Server's working space, right? And to be clear, sorry, this is only SQL Server. I do not know about this behavior in Postgres or anything else. Specifically, SQL Server is what we use. So transaction log is basically its working memory. As it makes changes, as you connect to it and update things, whatever, it adds into the transaction log and uses that to apply to the actual database. It's an internal concern, and so SQL Server will clean it up over time. It'll essentially garbage collect it. It will not clean up the transaction log while you have an open transaction. Fair enough, it can't really make a reasonable decision about what's safe to remove. So we had essentially stopped it from cleaning this thing up, and after 10 days, that was enough that the database just gave up and died. So what we had done was we had used pessimistic concurrency. Pessimistic concurrency controls are a control where you ensure that you have the ability to mutate an object before you try to do it. So something like a mutex is a pessimistic concurrency control. You're pessimistic because you want proof before you try to do the thing. You don't really think it's going to go that great. When we built the cluster-wide mutex, we modeled it as essentially taking a lock on a row in the database that represented that server task, where that server task represented a deployment. And the thing that was really nice about this for us was when you're building these kind of, I guess, like shared application level things, you really want to be thinking about the failure modes. And the failure modes of a transaction-based mutex were that if a server node went down, we all know it's going to happen, it would behave the way developers already understand a transaction behaves. The SQL Server connection will die, and the transaction will be rolled back. The changes will not be applied, and eventually, that hold on that resource in the database will fall open when it dies. And so this was great. This kind of gave us what we wanted, and it was something that we all kind of understood how to work with. So this is what the code looked like. This is literally a screenshot from my IDE today. We grab the mutex. As you can see, if you know C#, it's an disposable, and then we do the thing, basically. We do the thing that's going to mutate the object. If you've been writing software for a while, you may immediately see the problem with this, which is that you have to rely on a developer to remember to write that first line to take out the mutex before you mutate the thing. Using a language like C#, obviously, I am a huge fangirl of C#, you do get a lot of sort of nice code analysis properties, right? Like you can see where an object is used. You can understand where the updates happen to it. But even then, you can't really use code analysis tools to tell you where something is mutated if you want to like defensively protect against developers trying to mutate something without taking out the mutex, because of our buddy raw SQL. And we'll talk about that a little bit past the line. So essentially, the whole exclusion, this control, requires developers to remember to put this line first. That was not a great outcome. We decided, look, this thing is going to fall over in 10-day-long deployments. And when we looked at it, we found that it was not being used consistently. There were places that did not respect the mutex. And if somewhere doesn't respect the mutex, then basically you're fucked because anything can mutate it. And it's very hard for us to protect against that, essentially. So we decided, look, we're just going to take this thing out, and we're going to solve this problem in another way. So, great. Problem 1 solved. That is wonderful. Let's talk about problem 2 and our next foray into pessimistic concurrency. This one, so that first story, I was deeply involved in that one, in the weeds. This one is more of a theory as to what happened. So if any of you can actually like listen to this and tell me what you think went wrong here, I would love to hear it because I'm still not entirely sure. The same customer came to us and they said, hey guys, the database failed over. What did you do? And we went, we fixed that. What do you mean the database failed over? Was there anything different this time? They said, oh, well, now that you mention it, actually, in this case, it wasn't the transaction log that filled up and forced the database to fail over. This time, it was the temp DB. All right, so it is another problem. Delightfully, this is what happens when you scale. You fix one problem, and one more 10-day-long deployment later, you find the next one, the next point of failure. And so it's very satisfying that we had fixed the other one. So this one, Halibut. You will have noticed Octopus loves a fish pun. Halibut is essentially a custom RPC protocol that we wrote to communicate between Octopus server and our deployment targets. That's a lot of jargon. Let me break it down a little bit. So you'll remember Octopus server, the node that runs the deployments, that is the brains of the creature. It communicates with our tentacles. Those are the agents that run on the machine. You can see it in this diagram, right? So we've got the node, we've got the remote agents with the tentacles running on them. Halibut is the name that we have for the custom communication protocol. RPC means remote procedure call. Details are not super important here. It is just a common machine-to-machine kind of protocol. And so this one we did actually model in the DB a little bit as well. But what we were trying to do was, when we are deploying to a particular target, basically every deployment is a lot of fancy and very useful and important wrapper around an arbitrary script. At the end of the day, it's just a script. And so we take a lock on the deployment target to stop us from running multiple scripts on this deployment target at the same time. No one wants to start cleaning up the packages for your brand new deployment before we actually start running it, right? So this one was a little bit different in the sense that we weren't trying to stop the specific problem of concurrent database updates. We were essentially trying to control the behavior of not executing multiple things over on our remote target. And the failure for this one actually happened inside Halibut, inside that network communication layer. So what we did, we had another style of Mutex where we modeled our exclusion hold on the remote target with a transaction in the database. But in this time, we were actually also using the isolation level of the transaction. So you may be familiar with database transactions where when you create one, you can say, I'm going to stop everyone else from reading this thing while I have the transaction open, writing to this thing, some mix of the two. So in this case, we essentially use those to give ourselves a little bit of flexibility around who. Oh, cool! I just messed up my earring. Great. Anyway, let's get back to databases. So we used this to essentially give us a slightly more fine-grained control over how we executed things in tandem. Again, using something developers were really familiar with, using database transaction isolation levels. You may also be familiar, and I have to admit, I don't know if this is a pure SQL thing. At Octopus, we hand-rolled our own communication protocol. We also hand-rolled our own ORM, our own object relational mapper. That is a whole story. There is an excellent blog post about it by our CEO. It's called Nevermore, not for the reason that you think it might be. But anyway, you should totally go read that. It is amazing. Anyway, point is, in the ORM, we can set a timeout on a transaction. And we did set a timeout on this transaction that was being held essentially by the communication layer, actually, on this target while we tried to run a script on it. And we sent it to int max by default. Turns out to be about 16 days. So about 6 days longer than our software can survive a deployment at this stage. So what happened essentially was there was a communication failure, but because we weren't sort of modeling it in a way that if that failed, it failed open, this failed closed. The communication failure happened after about 2 days. Again, remember, same customer, 10-day long deployments. I don't know what they're doing. It happened after about 2 days, and we just held on to it, and we would have continued holding on to it for about 16 days until it actually timed out. I'm not sure exactly how that got around to filling up the tempDB. This is the part that if anyone knows, please tell me. The tempDB is another internal SQL Server concern. So SQL Server, if you are, for example, making a temporary table or assigning a variable or something like that, it stores that data in its tempDB. I have a feeling that what happened here was that after 2 days, this communication thing failed, and so the deployment just hung. And the customers didn't necessarily notice because they were used to it taking a long time. And I suspect that somewhere we were just backing up all of the other things that we wanted to do to this deployment target that we couldn't do because we were waiting on this one small step. And so I assume that's sort of how it ended up blowing up. But this was a case where pessimistic concurrency failed us, essentially because the way that we had modeled this one failed, closed, not open. So yeah, in this case, again, not a database update. The fix that we did for this one was really different. And this is one of the things that I really love about working in the server at scale team, is that we have a remit to touch whatever we need. So while we weren't able to pinpoint exactly what went wrong such that the database failed over, what we ended up doing was we decided this would be addressed, and as far as I know, it has been addressed by some changes that we were making to Halibut, such that we identified network errors. We identified them before things timed out, and we retried them. That involved a lot of work in making our tentacle idempotent, essentially saying that if we were to retry something, it will have the same impact. It won't be a problem if, for instance, we were to run the same script twice. And so, as far as we know, that one has actually fixed it. Which is not a very satisfying conclusion, unfortunately, but it is the one that we have. So let's talk a little bit about more about what I mentioned before, very briefly, this idea of hung deployments, and then the point at which we gave up on pessimistic concurrency and decided to embrace the promise of optimistic concurrency instead. So this one has even less data to back it than the last one. This is an anecdotal customer problem. They call us up and they say, hey guys, the deployment is doing nothing. It has hung. It has been in one state for the last 3 days. No, it's not. It's not something that we did. It's something that you did. Anecdotal problems are very hard to fix. And again, often this is happening in customers who are running our software themselves. We don't have telemetry. We don't have error logging. We don't have access to much at all. And in fact, even in our cloud environment, things are incredibly, incredibly locked down. Because I'm sure you all can imagine exactly how sensitive access to your deployment processes and your secure variables and secrets and stuff in there is. So this anecdotal problem was essentially, hey, deployment gets stuck, will not progress. This brings us back to our buddy, the ServerTask. So the bursty nature of the software is such that when we are doing all these arbitrary bits of work, whether we're picking up all of the packages, whether we are starting to deploy out the different releases to the different targets, we tend to have a hierarchical model of the work that needs to be done. Essentially for a deployment, if that deployment is, for example, to a single environment, to multiple tenants within a single environment, it all rolls up into a single server task. And that server task has to be the entity where we represent the overall state of all of these complex things, with all of the multiple ways that things can fail and sort of fail and maybe wait for a bit. And so we were getting race conditions in the server task. So similar to our beautiful initial race condition, deployments would complete. One would update the state. But looking at this, for example, if you imagine thread 1 having changed the state, thread 2 could absolutely overwrite that. And in fact, here's a diagram that is meant to represent this. What we found was happening was that the state would get corrupted. Let me talk you through this diagram a little bit because it's not as clear as I wanted it to be, but this is hard. So we've got a deployment. In the middle, you can see there's that server task. That's essentially the guy that knows about the overall success and failure and everything in between of our deployment. And you've got M1 and M2. Imagine those are machine 1 and machine 2. Those are our deployment targets. So as they kick off, they pick up the original ServerTask state. Let's pretend that it has a state of in progress. We're going to say machine 2 fails. The state is set to fail. We go ahead and we write that to the database. But very little time later, machine 1 successfully completes its deployment onto that machine, and it writes it down, and voila, our server task now looks like it's succeeded, even though one of the machines has failed. And there is no sensible way for us to continue from here. So the deployment just sort of hangs around, doesn't do anything. This turned out to be incredibly hard to detect. We wouldn't be sure at which point the state was getting overwritten incorrectly. We weren't sure where it was missing the updates, and it was very, very hard to replicate locally. And so we said, you know what, this whole pessimistic concurrency thing, this is not doing it for us. Let's have a go with optimistic concurrency. Optimistic concurrency is basically YOLO, I'm going to update, you tell me if that's a problem. So we go ahead, we try to, in this case, update the database, and if it fails, that failure bubbles up as an exception all the way back to the calling code, which allows you to handle that failure in your application, in the business logic layer, where you can make sensible decisions about it, right? Where you have all of the context to know what to do. And so in an effort to fix this, we went through absolutely everywhere that we mutated the server task state. Like I said, this is one of the fundamental building blocks of our software. There were a lot. There were a lot of places. And so we looked at every single one, we audited them. We found all of the places even that it was being updated in raw SQL, where we can't use, for example, like our IDE to tell us that a particular object is getting mutated. And so we figured out how to handle each of those. All right, a little bit early. We figured out how to handle each of those based on what it was doing. And in fact, we were a little worried that there would be a lot of places that we wouldn't be able to sensibly handle a failure. But what we found was there was actually only one place where we had to give up, and it was an API call. And so we made our API return a 409 error, whereas previously it would have quietly overwritten your state. So that was kind of nice. It lasted in production about 6 hours before we found that it was failing a lot of deployments. Do you know what is worse than a hung deployment? It is a failed deployment. So our cloud team saw our deployment failure rate in cloud go right on up, and they said, you guys just released this thing, you know what, we're just going to turn it off. And they were absolutely right that it was on us. And so the way that we had tried to use optimistic concurrency was, if we go back to our diagram, where we've got our 2 different machines and our server task, this is a very common thing that most ORMs do. I assume I've been corrupted by Nevermore at this stage. It will take a row version, which is essentially like a high watermark of changes, right? So when you read in your initial server task state, at the point that you've done your calculations, that you figured out your updates, at the point that you go to write back, if the row version has changed, this fails, right? And so what we were doing was we're bubbling those failures up, we were handling them, we thought it was going to be great. We had not expected the scale at which this happened. And this was because we had kind of not realized that the server task was stomping on the state so much. If you recall my example, you might be fanning out to, what was our first number, 16,000 targets. There's going to be a lot of concurrency when you're handling that. But if everything is down your happy path, if everything is going green, it's succeeding, these updates aren't going to stomp on each other. It might be a bad update, it might be bad data, but at the end of the day, it's still just updating it to succeed it. Unless you turn on row version, and then it goes, nope, this is bad data, I'm going to throw. And so we found that this was happening a lot more than we had expected to happen. And even with all of the retries and all of the care that we had taken, it still ended up with customer deployments failing, where previously they wouldn't have, right? From the customer's point of view, there was no reason for this to fail. This was all on us. And this was because of the assumptions that we had made about how often this thing was going to get updated and what the behavior would be like when it did. Oh, all right. So, optimistic concurrency was not quite working for us, at least not in that case. And there was actually a pretty good reason for this. Octopus is full of a lot of really, really smart engineers. The principal engineers had written a target architecture for us, which was essentially a description of how we should build software, what we should aim towards in our architecture, and why these things were important. And so my team, when we were looking for a solution to this problem, we had seen the optimistic concurrency section, and we went, heck yeah, that's us. We're gonna do this optimistic concurrency thing. Look, it's right there in the target architecture. We're gonna do it. We ignored the little coda at the bottom that said optimistic concurrency within a well-designed domain object. And that turned out to be really, really important. So let's talk a little bit about domain-driven design. Look, I'm not an expert here. This is something that I'm absolutely learning about. But what I understood from them to say was, sorry, quick aside on what domain-driven design is. Basically the idea that as a software engineer, when you are building out your application, you are thinking about how you design your model according to how the humans think about and speak about that business domain. And you take those ideas and you use them within the code so that your understanding of the code and the way you build the code maps to the human understanding as well. There's a lot more to it, but to me, essentially, that's what it is. And so this kind of raised the question for us of what is a server task? What even is a server task? It isn't a necessary part of the business domain. It had actually become a conglomeration of a bunch of different things. It was a piece of work that is executed. It was an item in a queue. It was the success and failure of a deployment. It was essentially an amalgamation of horror at the end. So, one of the other really important concepts that we hadn't applied that well from domain-driven design is that of invariants and aggregates. It took me a while to understand what an invariant is. Most of the, not gonna lie, like 3 different explanations went right over my head. This is the one that helped me understand it, which was essentially that an invariant is any logical rule that has to be obeyed throughout the execution of your program, and it can be communicated to a human, but not to a compiler. So let's take our ServerTask example. Let's take our state. When you are updating a ServerTask, if it has children ServerTasks, if any of those has failed, then the parent ServerTask state must also be failed. And we can't quite convince our compiler to do this for us. We have to do this in logic. I mean, maybe you're smarter than I am. Maybe you can find a way to do that. Regardless of this, this particular example, this is the idea, right? It is something that you need to enforce within a boundary that isn't necessarily something that you can do sort of automatically, right? You have to write some logic to do it. And so coming back to our idea of these domain entities, these things that represent a human-facing concept, an aggregate is like a bunch of those smushed together. I stole this quote from Martin Fowler, very, very smart software engineer who's written a bunch of great stuff. An aggregate is a basic element of transfer of data storage. So this is the bit that bit us, right? We needed to be making decisions about the state of the server task, and we needed a few different things to be able to understand that. And so the aggregate concept was we had smushed together a bunch of things that didn't need to be together, where actually we should have streamlined our aggregate to only be the things that we needed in order to enforce that invariant within its boundaries, right? the things that sort of need to be updated together. So the solution here was to pull apart the server task, basically. We had a bunch of unrelated entities. One that is probably something that a lot of you might do by default. But when we were looking at the children tasks of a server task, the way that we modeled it was with a count on the parent server task. So every time a new one kicked off or one completed, we would be updating that count. And along with it, stomping all over the status, right? This was something that we could model in our brave new world of actually having a real relational database instead of a document database stuffed into a single column in SQL Server. This really reduced the number of reasons that we had to update. That was one of the things that we pulled out, right? And the things that we extracted, we were able to remove because we didn't need them to enforce those invariant rules. We could update them independently. So I'm sure the really smart people among you will be listening to this very unsatisfying explanation of how we fixed it eventually and saying, but you didn't fix all of the concurrent updates. You have reduced the likelihood, and that's going to have a combinatorial effect. So it will be, be pretty good. It'll be a good customer experience. But you haven't actually solved this with the changes that you're making. You are absolutely right. And this is kind of the key part for us about scaling and about how we scale. And it is the decisions and the trade-offs we make about the amount of effort that we invest in the solution to fix this thing that is hitting our customers right now. Like, the delightful people saying, hey guys, 10-day long deployments, please make the database stop falling over. We needed to solve those. We needed to get over that hurdle and let that customer keep deploying, keep building their business. But we were also aware that the way that we had built this and designed this was inherently subject to these problems. So we rebuilt it. This is also deeply, deeply unsatisfying to me personally, because one, it is my sister team doing it. I have not contributed anything to it. But just aside from that, we haven't completed it yet, right? We are working on it, and we're working on these two things in tandem because they both have a lot of value. We have iterated and we've learnt a bunch about things we would do differently. But we're also aware that the fundamental nature and the fundamental scale of what we do has changed. And so we're targeting rebuilds around some of the stuff, while also trying to support our customers and keep growing in the meantime. One of the reasons that this has been really valuable for us is, you may recall that I said that concurrency and correctness are essential complexity for us in this domain, and it's true. And so it means that whenever you are changing how your deployment execution pipeline works, you do it very, very slowly and very, very carefully, and only as little as you can. So ideally, we would have been able to solve this problem a little bit more thoroughly, and we wouldn't have to include this in the things that we're rebuilding. But I like to think of it as like a beautiful, happy future where we probably use something like event sourcing for managing the state of the ServerTask object. But I can't guarantee anything like that. So yeah, sometimes you got to do both. You got to do the annoying toil, but you also have to do it to understand exactly what the problems are, how they can and can't be solved, and to justify the value of investing in this rebuild and being able to support your customers at their current scale, at your current scale, in the meantime. Thank you all so much.
Thank you, Alex.
Any questions? Yes, that was quick.
The question is, why don't you just do stuff in person?
Sorry?
I mean, why don't you just do stuff reverse? Like, anyway, it's just a sequence, it's just a task by task. Why don't you just make every task only be aware of what must be happened before that task, but not be aware of what will be happen after that task. So all the tasks is just kind of like watching what is before it. After what must be before it's done, you just do it. So you don't
Yeah.
say like,
No, I think I understand. So you're sort of saying that why are we doing so much in the task that we can't make it small enough that we can kind of interleave them?
No, I mean, if you go back to the slides where you have a parent and you say the parents must be failed if one of their child failed, right? But why would we use structure your task like this way? Like you got parents and you got your child. I don't think, but if you think it in a different way, like there's no parents, there's no son, there is just a task before me. And I execute it just right after all the tasks that must be executed before me, and I execute. You wouldn't be having the parent as some problem.
So three things on that. One is that these tasks are not entirely independent, right? So the things that we are doing, we have to be able to change the execution of things, change what happens. If, for example, one of them fails, right, we want to stop deploying out to other things. So we still need a way to understand what's going wrong if one thing has gone wrong to stop the execution of other things. In terms of why model it that way, I mean, yeah, that is one of the first things that we pulled up, right? We changed the way we modeled that relationship, where we moved the essentially the foreign key reference onto a server task. It now refers to a parent instead of the parent having that. That was one of the optimistic concurrency things we did. And additionally, that's what I mean about event sourcing. So I don't know if you've heard the term event sourcing, but essentially event sourcing is the idea that you don't really store a property. When you go to look at a property, you compute it through the history of other things. And so that's what I mean when I said it's likely that the answer here in the future is going to be that event sourcing one. Yeah.